Okay, so before we start, let me just give a bit recap of what we did yesterday. Can you hear me fine? Okay, so just a small recap. We have introduced yesterday a lot of concepts by starting from the example of the Heisenberg model. And the concept we introduced were these monodromy metrics and transfer metrics. So an important step that we reached yesterday was this result over here that tell us that for integrable model we can always construct this object called the transfer matrix, and for different value of this parameter, this object will commute among them. Now let's take one of these objects, and I was mentioning you that we can always expand this. And if all of these parameters are equal to 0, then in the expansion we get some quantities which will be local. So we can write them. Sorry, there is some echo. Maybe I will try to move. Okay, I can. Let me move it. Okay, let's see if, yeah. Okay, so I was telling you that if we expand this, then we get these quantities, and these quantities are local if this condition for the R operator works. What I mean by local is that this Qi, I can always write as a sum over density, and these densities will act on some site J, going from j to j plus I minus 1. What I mean by this notation is really that if it's Q3, then it will only act on 3 sides of the chain, Q4 on 4 sides, and so on. So this will be my shorthand notation instead of, because for Q7 I would have to write up to 7. I'm not going to write all these charges, but just in case.
Can you please write slightly bigger? Because the indexes are not visible from the
Sure, I will, yeah. So this j plus 1, j plus I minus 1. So an important results from yesterday were this relation over here, and then the fact that all these are analytical functions, so we can always take the log of them and expand it, and we get this property. This is one of the main definitions of integrability that I was giving. So having an integrable model means that we have an extensive amount of operator that commutes among them. So just to summarize, what we did was to show that from Yang-Baxter equation, then it follows that the charges Qi, Qj will commute. So what will we do today is the following. So first of all, I will continue from the lecture of yesterday, and I will set all of these ui equal to 0. And I will give you the physical meaning of this charge Q1. Then Q2 was given yesterday in the tutorial by Laura. So this Q2 is the Hamiltonian of the system. And I will also explicitly write you what is the expression of Q3. The derivation is a little bit long. I reserved for the end of the lecture, maybe when we are tired, so if I make mistake, you don't notice. But I would need this because in the afternoon, what I plan to do is to tell you, like an analytical way to check if you have a given Hamiltonian, if this Hamiltonian belong or not to the Yang-Baxter class. So yeah, I encourage you, if you are interested in this topic, to attend the tutorial. And in the tutorial, I will also tell you if you want to construct from scratch an integrable model, how you will do. But to do that, we need the analytical expression of the charge Q3. Okay, but in case, you can just believe me and then we can continue anyway. But let's see what we do today. So the proper, part 2 that I was mentioning yesterday, I will give you the definition of a quantum circuit as a many-body evolution in discrete time. And I will define when a quantum circuit is Yang-Baxter integrable. And then at the end, I will tell you how to connect the lecture of yesterday with the lecture of today. So how to systematically construct a quantum circuit which is integrable using the transfer matrix approach. Then also yesterday there were a lot of questions about open boundary condition. So this will come in the third lecture. We are gonna construct all the integrability machinery for circuit with open boundary condition. And then in the fourth part, I will give a sketch on algebraic Bethe ansatz, just to show how all these concepts of integrability really play a role in understanding the spectrum of the theory. So if there are no further questions, yeah.
Suppose I am able to identify these QIs, okay, a set of operators that satisfy this commutation.
Yeah.
Is it guaranteed that there is an underlying structure of the XOR?
So you want operators that are local or not?
Suppose by some magic I am able to construct some local operators that satisfy that algebra, that QI, QJ. Does that mean that there is an underlying Yang-Baxter equation?
So in general, I don't know, but I will show in the afternoon that in some cases you may be able to recognize this structure. But I am not aware of any spin chain where the conserved charges are local, but they don't have a Yang-Baxter interpretation. Like sometimes model can be really complicated. You can get some charges, and then if the charges are local, it's easy answer to say no, it is not Yang-Baxter integrable. Like I think Gabriele yesterday mentioned about this cellular automata called the Rule 54. At the moment, we are working on a quantum deformation of it, and we proved that there is an algebraic structure behind, but the structure is so complicated. So if I would have a bet on it, I will say no, it's not integrable. So I will be very, very interested to find a case where it exists, these charges, but is not Yang-Baxter integrable. But to prove negative statement is harder than to prove positive one. But if the charges are not local, then there exists some case, something called, for example, this okay, I'm not sure how to spell, Inom-Semsev spin chain, where you have the charges, but I don't think it exists an algebraic structure. Yeah.
So before just you define this Lax operators through the RLL equations, and for our case, this auxiliary index is C2, as the same as the physical one.
Yeah.
Then the RLL just boils down to YBE.
Exactly, yes.
So if it's not the case, it belongs to some V which is different than CM, then how the Lax operators are different than the R?
Yeah, so thank you, because I forgot to mention. So in this lecture today and tomorrow, we will work always in the case where the auxiliary space and the physical one are the same. The reason why I gave you the more general expression is because in principle, if you have an R matrix, there is a lot of group theory behind, and which I obviously won't have the time to talk about, but you can change the representation of one of the two space and get some different object, which will still allow you to have to compute all this quantity, like the transfer matrix and so on. But and also, like, there is a bit more, because if you use the Lax operator, then you cover a broader class of model. Like yesterday, there were some questions on medium range model that are model where the Hamiltonian is not acting on two sides but on more, and these also can be taught in the same spirit as with the transfer matrix approach and so on, but for that you would have to use the Lax operator, not the R. So the reason why I gave is just because maybe in the literature you will find it out, and then you can find some connection. But for us, we work on the simple case where the two spaces are the same.
Okay. I'm sorry, I will interrupt that. So another thing, so this for this X-axis model, it possesses this SU2 symmetry. So this SU2 is underlying these R operators, or it will pop up in some constant charge?
Everything will have SU2 symmetry, yes. So the R matrix has also the Hamiltonian and all the charges as well. Yeah. And yeah, thank you, because this is the power of all these methods is that at the very end, we will be able, with this algebraic Bethe ansatz, to compute eigenvalues and eigenvectors of the transfer matrix itself, not of the Hamiltonian only. So we will be able to compute an expression of the eigenvalues, and then by taking higher order derivative of the log of this eigenvalue, we get eigenvalue of all the charges basically for free. So this is another point where this approach is useful. But let me give you some feeling on what are these charges, and then we go to the main part of the circuit. So let's understand what are these operators. This will be general for any kind of model. So what are Q1, Q2, Q3? So this will be very useful to make the final connection between the Hamiltonian of Heisenberg and the R matrix that we talked about yesterday. So Qi, let's focus on simple case of L equal to 2. And let us consider the R matrix R0J U equal to U identity plus IP 0J. And we will strongly use the regularity property that R0J at 0 is proportional to the permutation operator, P0J. And for simplicity, let me put equal to the permutation, because as I was mentioning yesterday, we are always free to renormalize this object. And Laura in the tutorial showed that is indeed the case. So if you have an R and you normalize, then it still satisfies the Yang-Baxter equation. So for L equal to 2, let's compute T0. So T0 is the trace over 0 of T0 at 0, and this is equal to the trace at 0 of P02, P01. Equal to, can someone tell what is this object?
It's P1.
Sorry?
P1.
Yeah, thanks. So this is P12. The way to see is that you put this operator at the very end, and then whenever there is a 0, since here there is a 0, the 0 becomes 2. Or you can also see it if you multiply by P02, P02, as you saw yesterday in the tutorial. So the P operator, the 0 space becomes 2, so this is P21, but permutation doesn't matter the order, so P21 is P12. And then we use also the property that the trace over 0 of P0I is equal to 1. So what is a P12? This is basically shift operator for length equal to, because we have T0, then we have, let's consider an operator A, which is acting only on one side, and then we have T to the minus 1 at 0. But this is just P12, A1, P12, which is equal to A2. So we can get a little bit the feeling of what is the transfer matrix at 0, because what this is just the translational operator. So let's consider the case for general L. Then this T0 will be equal to the trace over 0 of, in this case, we will have P0L, P0L minus 1, and so on, up to P01. But we can play the same game as we did for length equal to. Now I will take this P0L and I'll put at the very end. So every time I have a 0, I have to swap 0 with L. So this is PL. Ask me if this is not clear. L minus 1, PL, L minus 2, PL, L minus 3, up to PL1. So what is this object? Let's consider L equal to 6, for example. And we apply T0. Then we can take a site, an operator acting on one side, I don't know, A3, for example. T minus 1 at 0. And this makes the same case. So this is P6, 5, 6, 4, 6, 3, 6, 2, 6, 1, A3, and then we have the inverse, so we will count from here. So P, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5. So what are these operators doing? P61, P61 square to 1. And I can square it because 3 is not, there is no overlap between these operators. So I can remove these, same for this. Then here, P63 act on this, so this site 3 will become 6. So we removed this, and then the 4, 6 becomes 4. So this is now A4. And we are only left with P65, P65, but this square to 1 because A4 does not overlap. So this is A4. So T0 is just the shift operator, which is a conserved quantity. And we are happy about it because we have some system which have periodic boundary condition. Yes? P, which?
Like P63
so I am using this property. So P, which one did you ask? 6,3? Yeah. A3, P63. So this is equal to A6 because the permutation operator is basically just interchanging site of your chain. So this, suppose you have length 6, so you have 6 Hilbert space that you can label 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. Now, A3 is only acting non-trivial in this space, but the permutation operator is swapping site 3 with site 6. So now this A3 will move here and it gets A6. So in general, the property is P, I, J, A, I, P, I, J becomes AJ. Yeah. Yeah, this is like the general one, and then you can specialize if this P, if this operator is acting also in two sites, then the same game up, and you just swap sites.
And L was general, you are writing T0.
Mm-hmm.
How did you write a P?
Yeah, so I'm writing T0 because this comes from the definition of the monodromy. So, and it comes from definition of monodromy, all UI are 0, and then I'm using this, are 0, yeah.
No, how spacing over 0 gives the PLL minus 1.
Ah, okay, sorry, yes. So, so this P0L, I want to put it at the very end here. So what I do is I take this and I swap multiple times. Yeah, clear? And then you use this. Yeah. Okay, so now, so this is T0. Let's see what is Q2. I will not do it again because Laura did yesterday. So the second one, Q2, this is related to the Hamiltonian in this way. So if we take derivative log t of u, this is just t to the minus 1 u, t prime of u, which is, and then we evaluate at u equals 0. And this is the sum from 1 to L of p I plus 1. Derivative of u are I plus 1 u for u equals 0. So this is a sum of range 2 objects, so I can identify this one as my Hamiltonian, H, I plus 1. And this is exactly the connection that we saw yesterday in the tutorial on how the R matrix of the Heisenberg model, which I wrote, is related to the Hamiltonian of the XXX spin chain. If you want to see it more explicitly, this is the Hamiltonian that we saw is J over 2 I derivative log tu at 0. And then I think we have to add some term proportional to identity, just to match exactly with the form of the Hamiltonian which I gave yesterday. But as I mentioned, this is not important because identity operator always commute. Okay, so just to write, because we maybe need, so the Hamiltonian I plus 1 is this pi I plus 1 derivative r I plus 1 u at u equals 0. And sometimes there is a short notation, PR is also r check. So in some of the literature, maybe the Yang-Baxter equation looks a little bit different with what I gave, because instead of r, it is used this r check. But it's exactly equivalent. But obviously, if you apply permutation, then the spaces will change. Okay, but now let's see what is Q3, because as I mentioned, I would need in the tutorial. So, yeah.
This Q1 is actually Q1, if I calculate, Q1 is actually log of Q naught, right?
Thank you, yes.
So, but that is the same as Q0 you were talking
Not, yeah, thank you for the point. Let me say. So, the relation is this one. So the first charge Q1, I'm saying that this is the P operator of quantum mechanics, and if you want to see, it is like this. So let's go back to the case of Q1. So the relation is, you can see it in this way. So let me see. Yeah, so for what happens is that in elementary quantum mechanics, if you have IAP, then x e to the minus IAP, then you get x plus a. And in our case, we can now identify this IP to be equal to t of 0. And then p will be exactly proportional to the log of t of 0. So in this sense, I'm saying that is related to the P operator of quantum mechanics. But if you want really Q1, you have to take the log of that expression. Yeah.
So can you explain Q2 equals to right-hand side sum over Pi du r u, how do you do it?
This one?
Yeah.
Yeah, this I didn't derive it here. It was done yesterday in the tutorial. So if, yeah, I can tell you later on better if you want. But the important part is that if you take TU, you apply the derivative once, then you use the chain, like you use the property of the derivative of product, and then you can identify this as a sum of range to object. So you get this density operator. And then since it's density 2, I'm identifying this to be my Hamiltonian. Yeah. And now let me go to Q3. I will not derive it because it's a bit long, but again, you can try, and in case I can show you if there are problems. So Q3 will be the second derivative of TU for u equal to 0. Also, you can find the exercise of the tutorial on the website, and this is also written there. So what is the derivative of TU? Over there you have the first derivative, so you can just take another time the derivative. This is minus 2 u, and then this is t prime u square, just taking derivative of this, plus t to the minus 1 u, second derivative of u, and then you evaluate this at 0.
That will be log of
Ah, yes, thanks. Yes, also there, no, yeah, there I put, okay. So I'm taking another derivative of that expression there, and I got this one here. Now this, what is this? This is exactly Q1 square, right? Yeah. So this is Q2 square. Yes. With minus. Okay, so if you take the derivative 2 times of the transfer matrix, you multiply by t minus 1, you will find the following, if I didn't make some mistake, but the overall structure should be correct. So this is I from, are the indices visible now? From 1 to L, then there is a commutator H, I plus 1, H, I plus 1, I plus 2. And then there are some extra term, plus. There will be a sum of Pi I plus 1, second derivative U of R I plus 1, U, from always 1 to L. And then there is minus sum H I plus 1 square from 1 to L. So I think this term can be easily understood because we are taking the second derivative. These terms and this one, they come because when you take the derivative 2 times, you have to take the derivative of each term, right? And then there may be some crossing term that multiplies. You can try to get this expression explicitly for L equal to 4. And some of the term coming from the second derivative will cancel exactly with this. So, yeah, I understand it's not very easy to see, but if you sit down and work it out, then it's probably more clear. But important point, this here is the object that is giving the range 3 contribution of our charge. I plus 1, I plus 2. So this is an operator A, which is acting on 3 sides, I plus 2. And then this one is like operator that are acting only on 2 sides, I plus 1. Then derivation of higher conserved charges can also be done. It is, of course, more involved because you take higher and higher derivative. But it's a very beautiful fact that any Qn, you can always prove that the part that contributes to the higher, to the density with the higher support has always this nested structure. So, for example, Q4, it will have a term which is I plus 1, then is another commutator I plus 1, I plus 2, I plus 2, I plus 3. And then there will be, of course, other stuff, but this other stuff will have always lower range. So this we can always get very easily, then the remaining part is not so easy, but it can be obviously done. Then all this calculation, of course, for small system size, you can do it by hand. Otherwise, you can program in Mathematica by using some non-commutative algebra, and you can teach Mathematica all this commutation relation, and you can get analytical expression. Okay, so I finished for now what I wanted to finish from yesterday. Yeah.
One question. So, if let's say I go to the higher order expansion, like I construct Qn, so the range of action would be like order n, like it will act on n sides?
Yes. So n, it will act on all your chain, but you can always write as a sum of density acting on n side. Because of the regularity property that the R matrix at 0 is permutation.
I'm thinking that, how long can you ensure that it's local charge?
You can ensure for any type, because how can I?
Finite system, so think of L equal to 4. 3 or 4 local charges will completely solve your thing.
Yeah, exactly. No, but I think his question is more like if you take any arbitrary system, how can I be sure that you can always do? I think you can So all these proof, as you did in the tutorial, for example, or also how I get this expression here, those are always done for small system size. Then you increase a little bit, and you see that the structure is very repetitive, and then you can guess how it is. No. So also this one, it has this form. So and for higher and higher, it become also nested. Now I cannot think of any. Like mathematical proof that will show that it is always like this, but if you try, it will work out. Or there is another possible way to derive these charges, which I won't have the time to mention, that is related to the something called the boost operator. So every charge that you have, Qi, plus 1 will depend in some way from Qi. If you apply this boost operator. So you don't actually need to take derivative of transfer matrix. You can just take your Hamiltonian, you boost it once and you get Q3, you boost it another time and you get Q4 and so on. And these two formalism match, so you get the same charge. So maybe this is one possible way to see that the charges are local.
So earlier we saw that this R of U is related to the Hamiltonian. Mm-hmm. Then you are telling that in boost operator formalism we don't need this R of U. Given the Hamiltonian, we can construct all the charges.
You can construct, yeah, but then if you want to do, I don't know, algebraic beta ansatz, then you would need to have the algebraic block. They are, yes. Yeah. Okay, so with this, yeah.
So while constructing Q1, I understand that it's just log T U. And why did you put U0 here?
Yeah, so all the expansion are always evaluated at U0 because all these Q1, Q2, Q3 are the coefficient of my expansion in U. So yeah, I forgot many times, but everything will always be in, yeah. Yeah, of course you have to first take derivative and then you set U to 0. Okay, so with this I conclude the first part. Let's move to the circuit. Okay, so first let's define what is a quantum circuit. So one, I will say that a many-body operator M is referred as a quantum circuit if it can be factorized into a finite sequence of two-particle operators that are called gate. So M, many-body operator many-body operator that can be factorized. So to give an example, for example, for if we take a system of length 6, 4, 5, 6, so this is 1, 2, 3, 4, 5, 6, I can construct the following circuit. I will explain all these blocks in a moment. And then I can tell, so these blocks are matrices that are acting on two spin, and I can write the time can go like this, and let me just use the same notation that I have. So this is UO, which means odd, and this is UE, even. I will now make the parallelism with the continuous time evolution, but just to say, so this is U odd, U even. So this, for me, is a quantum circuit because I have many body operator and it factorizes into block of 2 by 2. But now, when can I say that a quantum circuit is integrable? I'll go up because... So a quantum circuit M is integrable in the same way we defined Hamiltonian if the operator M, which describe your dynamics, commute with an extensive number of quantities. So part 2, integrable quantum circuits. So now I have M, which commutes with this Qi equal to 0 for every I from 1 up to infinity. Now, this will be my definition of a quantum circuit, but if we want to construct a quantum circuit from scratch to be integrable, then things are going to be really, really complicated. So this has been done in the reference which I gave yesterday, this PRL by Thomas Prosen, Lennart Zadnik, and Mathieu Vanica. They made the so-called, is called integrable trotterization. So what they did was to show that this M can be obtained from a transfer matrix itself. And then you can, I will show how, but the idea is that if you have M, and this commute with Tu in some way equal to 0, then we are done, because this Tu we can expand, like, or Tu or log of Tu, we can expand in Qi plus U, Q2 plus U squared, Q3, and so on. So if we manage to find an M which commute with log of Tu, then we are happy. We constructed a circuit that is integrable, because this commutation relation works for any order in U. And this is exactly what they did in that paper. Let me try to...
You showed that all type of transfer matrices, TU, TV, they commute among themselves, but M cannot be interpreted as a transfer matrix itself, something different also.
Exactly, no. So this is exactly what I will do now. I will tell you that we strongly use the fact that Tu, Tb commute among themselves, and we will write M as a function of the transfer matrix. So, and then we are done, because M is just in one point, but then Tu, Tb commute for any point. So that's, yeah, that's the key. But before going to the part, I want to just tell how to go from this discrete time to the continuous time. In a second. Are there questions?
So when can you factorize the many-body operators to
Sorry?
condition to that?
Can you repeat? I didn't hear.
What are the conditions that the many-body operator have to satisfy to be separated into the two-body operator?
Yes, I will try to tell now how to get this. Yeah. So this, for now, you can take it as a definition, but it comes from this. So consider a local Hamiltonian H that you can write as the sum from 1 to L of j plus 1. Then we can consider U as e to the minus I tau h. And we can write h explicitly, so this is minus I tau h12, h23, h34. I think we also saw this. This is called the Trotter expansion. We also saw in the in some of the tutorial by Giacomo, and maybe in some other lecture as well. 34 plus dot 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 h L1. Now what we do is we rearrange this order in the exponent. So we have e to the minus I tau, h12, h34, h56, and so on. Plus, now I'm not doing anything because the sum we can always swap order. So this is h23, h44, 5, 6, 7, and so on. And now we make the one approximation. So we say that this is approximately equal to e to the minus I tau h12 plus h34 h56 and then e to the minus I tau h23 plus h45 h67 plus other term. Now I am neglecting term of order tau, right? Because this rearrangement I can always do because I am in the exponent, but then if we want to do this, we would also need to add some commutator between the various terms. So this is then equal to e to the minus I tau h12 e to the minus I tau h34 and so on. So this will be one block. And this is e to the minus I tau h23 minus I tau h45 minus I tau h67 and so on. And now we can say I will call, this is okay, right? This is exactly, not approximate, because all these commute, yeah. So this is, I will call this U12, this U34, then I didn't write U56 and so on. And this is U23, U45, and so on. So this is now our evolution operator U, and we can represent into this block that I was drawing before, exactly in this way. I can refer to this one as U even. I call it even because the first site is even, but it's convention. And this one we can call odd. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And then we have even, odd. So what is U even? U2, 3. So there will be a gate acting here. U4, 5. There will be a gate acting here. And U6, 1, because we have periodic boundary condition. So let me say we restrict to the case of L even. In the one exercise of the tutorial which won't be solved is to check what happens in the case of L odd. Also in the relation with the integrability. So maybe you can try and in case we can discuss. And then the second layer will be U odd. So U1, 2, this and this. So this will be the graphical representation of this one.
Even though using periodic boundary condition?
We are, yes. So yeah, so this is the periodic part. Yeah. U61. And I will also use the simple case that Uij is equal to Uji. Yeah, I will tell in a second that this U is actually related to our R matrix. And also R matrix had this property that we can swap indices. But okay, let's now go to the main point. So up to now, this is general. I didn't use integrability at all. I just used the fact that the Hamiltonian is factorized into two-body operators. So now I want to use the...
Choosing tau, so this requires choosing tau to be small. So then suppose I choose tau to be dt, where dt is small. Then the evolution step comprises acting on both this U, E and UO.
Exactly, yes.
So first I do, or whichever way I do, I guess. It doesn't probably matter.
No, it doesn't matter, but
okay.
yeah.
UE, UO, that's one step. And then UE, UO, UE.
Exactly, yeah. And the error you are doing is linear in tau.
Yes,
Yeah.
So even and odd, do you even and odd, do they commit?
They do not.
So in this way, we also define it the other way, right? First I do odd and then even.
Yes, exactly.
Bit of arbitrariness.
Yeah. But then you have to be consistent on what you define. Like I will show now that with this choice we get this particular mapping with a transfer matrix. Otherwise we would have to swap the sign, but it's nothing. Yeah. Exactly. Yeah. And then you forget and you change it afterwards. But in principle, yeah, you can define as you wish. Okay. So now let me just, when yesterday I was defining the transfer matrix, I told you that all these parameters, U1, U2, UL, are all arbitrary. And if we had U equal to 0, then Q2 is exactly the Hamiltonian. But now, what is the choice of these parameters in order to have a circuit? And the choice is this. So consider L even. We can construct the arbitrary transfer matrix TU. This is trace of R0 L U minus UL 0 L minus 1 U minus UL minus 1 up to R0 1 U minus U1. I make this choice. I fix U to I, so all the even one I fix equal to kappa, and all the odd U to I plus 1 I fix equal to minus kappa. So what happens? TU is then trace over 0 of R0L U minus kappa 0 L minus 1 U plus kappa dot R02 U minus kappa R01 U plus kappa. Okay, so this is just a definition, and for what we saw yesterday, TU and TV commute always. But let me say the relation between R and U. So what we will use that U I,J is equal to R check I,J at the point 2 kappa. So this is permutation I,J R I,J 2 kappa. Okay, and this was the definition of R check that I gave before. So now what do we do? Consider the case, a simple case of L equal to 6. I will show you that the operator M, written as U odd U even, is equal to the transfer matrix to the power minus 1 of minus kappa, and then the transfer matrix evaluated at the point kappa. But then, since we know that the transfer matrix for any point TU, TV commute, then we also know that M commute with TU equals 0. And then we are happy because we constructed a circuit with infinitely many operators. Is the logic clear? Then, I mean, it's a matter of computation on how to get it.
Why this UIJ has to be PIJ and RIJ? It's UIJ.
As
Why the equality board?
Okay, yeah, so this I will take as a definition of my dynamics. I will take the R matrix that we had. And for the Heisenberg model, you can actually check that the R matrix that I gave can also be obtained if you take an exponential of the Hamiltonian, which I also gave. So it's every two formalisms are consistent. So for now, this you can take as a definition of your dynamics.
So this R check, this multiplication has to be unitary, and that can be done because you showed that this unitarity can always be.
For Heisenberg, it can be. Then now,
generic model, UIJ has to be unitary.
Depend on which dynamics you want to study. So if you want to study unitary dynamics, you want to construct a unitary quantum circuit integrable, then you pick U to be unitary. If you want to study a circuit which does stochastic dynamics, then you pick it stochastic, or you are free to choose. You can also use the circuit to model some open quantum circuit, then the dynamic will be dissipative. So you can take in the next lesson, we will use some circuit with open boundary. So you can, for example, take your gate to be unitary, and then you break unitarity with some term to the boundary, which can be some action with your system with some environment. So it won't be unitary anymore. The only important part to construct a circuit which is integrable is that this is a solution of the Yang-Baxter equation. And then it's really general for any type of model. Yeah. Okay, any other question on the logic?
How do you write your A equals to U0 UE, EO and then how do you get this T inverse?
Yeah, so these I haven't derived it yet. I just wrote it. Yeah. No, just, okay, because now I will prove this, but since it's a little bit technical, I want to make sure that the logic is true, that the definition of having a circuit which is integrable is having the operator M with commute with infinitely many charges. And so since we have this, also like any function of TU will commute with TV. So if I prove that M can be written as some function of my transfer matrix, then I am done.
I think he has the same question. How did you write that?
This you can take as definition. Yeah, so for Heisenberg model, you can show that they are same. You can take Hamiltonian that I gave, you exponentiate, and then you get the R matrix of Heisenberg up to some massage, but it's the same.
K will be depending upon the K.
Which K? This K? No, this kappa is an arbitrary parameter. It will be related to the time tau. I will show at the end that this kappa is related to tau. In particular, I think it's tau is equal to 2 kappa. Yeah.
So here the lax, so even if this auxiliary indices has a larger interface, this will not be replaced by lax because this is a physical index, right? So this Uij, even if I consider the XSS model with auxiliary index very large, the higher dimension representation, in that case, R is not replaced by L.
So you can construct a circuit also with the lux. For example, you can construct this medium range circuit if you use the lux, and then you say that my U operator is equal to the lux itself. Because at the end, we trace out the 0 is not there anymore. This is a quantity which depends only on physical. Yes?
So this lax has to be a solution of RL?
Yes. Yeah, this is the only thing that we use. You can construct circuit if R is a solution of Yang-Baxter or lux is a solution of RLL. Yes. Yeah. Okay, let's show this explicitly. So we take length 6. Let's try to be careful. So TU for U equal to kappa. So what this is? This is a trace of 0. Then we have R06, U minus kappa, so R06 at 0 is just permutation. I'm not, okay, maybe I should write R06, U minus kappa, 05, U plus kappa, 04. If it's too slow, and I can speed it up a little bit. Is okay? Okay, yeah. 03 U plus kappa, 02 U minus kappa, 01 U plus kappa. Okay, so for this is general. Now for U equal to kappa, this is trace 0 of P06. I am now taking this and evaluating at u equal kappa. Then we have R05 at 2 kappa, but this is just P05 U05, right? P is this. This is R, yes, correct, because this will be R05. I can write it as P05, R check 05, and then I can use R check equal to U. Okay, so this is P05, P05 U05. Then there is this one, which is P04. Then there is this one, which is P03 U03. Then there is P02. And then there is P01 U01. Okay? Now, we want to work with this permutation operator in order to remove the site 0. So how do we do this? We can do, for example, we can, let's try to put all the u nearby and move all the permutation in front. So if I move this permutation here, what will I get?
Just one question.
Yeah.
What are those U06, 04? Why did you put those?
No,
Because
because
I am taking this, and whenever there is a 0, I just substitute as P. Wherever there is a 2 kappa, I substitute as 0. Yeah. So, okay, now if I move this here, the site 0 will become 4. So this is P04 U45. I just moved this here. Now here I take this and I move here. And this is U23 P02. Okay. So if this is okay, then this is trace of 0, P06, P05, P04. Now, P03 I can move before because it will commute. Then P02 as well. And P01 as well. And then I am left with all the U's. U45, U23, U01. Is this clear? So I am just using the property of permutation to move all the permutation nearby. Now the last bit, I will take this permutation and I will move at the very end here. If I do this, all the 0, wherever there is a 0, it became a 6. Yeah. This I take it as a guess. Like I am telling you that if you take the transfer matrix and you take all design homogeneity to be alternated, then your M operator can be written in this form. Now I'm just showing that this is indeed the case. But yeah, I can tell you later how to map also for different type of geometries if you want.
So this is not, this particular function is not always guaranteed. That's what you mean. I mean, you mean that this, so you are trying to write down M as a function of your transfer matrix.
So now I will show you that if you have this kind of geometry, with geometry I just mean how the gates are placed, then you can always write in this form. And this, but this kappa has to be, like the UI that we had has to be alternating kappa minus kappa and so on. And then this is, everything we are doing is correct just if R is a solution of Yang-Baxter, is not model dependent. So if now this is the case, we can take this P, we put it at the end.
One doubt, like the solution of the Yang-Baxter equation
Uh, sorry?
R05
Mm-hmm.
to K, you wrote P05 U0.
Yeah, because I use this definition. I am telling that.
R0 P.
Is there some
No,
type of?
R05 to K.
Mm-hmm. So.
P05 R05 to K.
Yeah, but then you can invert it, no? I mean, it's just act upon
You can, because permutation square to 1, so you can move it. Yeah. Yeah, those indices, I mean, it just takes a little bit of playing with this permutation, then it's. So now I am moving P06 at the very end, and wherever there is a 0, this becomes 6. So this is P65, 64, 63, 62, 61, and then U45, U23, U61, and then the trace over 0 of P06. But this is identity. So you can start to get a little bit the feeling. Now this is close to U34, U23, U45, and so on. So then we will put the piece together. So these operators, they will all commute among them because you can see it because the indices are different, or you can see it also from the gate. There is no overlap between them. Now let's do T for U equal to minus kappa. And let me call this is the shift operator that we had before. So I'm going to call this capital P. So T to the minus kappa, this is the trace of 0. Same thing, now we use this definition. So this is P06, R06, check to the minus 2 kappa. So what I am doing now, I am using just the definition that R is equal to PR check. So P06, here this is R to the minus 2 kappa. Then what do I have? Anybody can guess? So we are taking this TU and placing U equal to minus kappa. So R05 at 0, this is just P05, right? Then we get P04, R check 04 to the minus 2 kappa. Then we have P03, okay. P02, check 02 minus 2 kappa, and then P01. And now we can use this other definition. So R satisfies this property, the R matrix. I forgot to show yesterday, but if you have R of ij of u, and you multiply by R ji of minus u, this is just identity. And in our case, we are working with R matrix that are symmetric. So I can write this as ij itself. So I can write this R check 0 j minus 2 kappa as R check inverse 0 j of 2 kappa, but this is just u because of the definition of u. This is just u inverse 0 j, right? Exactly, yes. So what we will get now, this t of u equal to kappa is just p, and yeah. No, just wanted to say that this t u equal kappa, you get p, and then you get this, which we called u even. Now, if we finish this will give us p times u odd inverse, and then we take the inverse, the two big p squared to 1, because we are shifting one side and then we are coming back, so nothing happened. And then we get m equal to tu minus kappa inverse tu. Okay, yeah.
So this property of this R matrix, Rij, U and J and minus U, is telling you that if there are two particles, I and J, the difference is U, so they will interchange the velocities.
Yeah, basically you can see it this way. But so this is general. It works for any Yang-Baxter integrable model. You can take Yang-Baxter equation, send v to 0, and then you will get this one. The only thing that we are assuming here is this, that we can exchange, Ij can be exchanged. If not, you can also do this game, but let's stick with the simple case. So let's put the piece together. Okay, so we can continue from here. So what is this? This is trace of 0, P06. Then we have U06 inverse. Then we have P05, 04, U04 inverse, P03, P02, 03, P02, U02 inverse, P01. We are almost there. Yeah.
The property that you wrote, like R0J minus 2K, will there be permutation of it comes with the end? Like, you have like U inverse, will permutation of it also be there?
Which one? This?
That like, yeah. The last thing. Will there be permutation operator there, or it's like that?
No, this, I think it's like this, right?
Because the above like R0 by 2K, you wrote P0 by U0 by there. So here like...
So I am using the definition. Oh, I am using the one at the very up. So Uij equal to R check. So yeah, I think it should be like this. Yeah. But yeah, please check, because there may be some typos in the way. Okay, so t equal to minus kappa. So now we want to do the same story as before. So we want to place all the permutation in front. And so I will swap these two, and this becomes P01 U12 minus 1. Then I swap this one here, and this becomes P03 U34 minus 1. And then I will swap this here, and this becomes P05 U56 minus 1. So we get trace of 0, P06, P05, 04, 03, P02, 01. Then we have U, all the U's, because I can put everything before, because there is no overlap. So this is U56 to the minus 1. Then there is a U34 to the minus 1, U12 to the minus 1. And now you can just put things together. So I told that M is T to the minus 1 minus kappa, T of kappa. So T to the minus 1 minus kappa is the inverse of this one. I have to do a little extra step.
This P times range. This P times range.
Exactly, yeah. So this will be P. Because, yeah, we did it already some times. So now this is, we take the inverse of this. This gets U1, 2, U3, 4, U5, 6. Then we have P inverse. Then before, we also got from here, we got P times U, what is this? U to 3, U for 5. Sorry? Yeah, so this will be the second row. And now this permutation commute, and we exactly got what we were writing here. So this is a way to construct a quantum circuit which is also integrable, because we are guaranteed that the transfer matrix commute. And we proved that the circuit dynamical evolution can be written as a function of the transfer matrix. So we are done. Some other questions?
So if you would have defined this N as Tk, T inverse, I mean the inverse of this thing, you have this even odd and then even. Right? The convention will change.
I think so, yes. You will have to, yeah, probably you have to, or you can say I take U equal to kappa inverse and then T minus kappa. You can try to play with this to check what you will get. And also, like, I suggest maybe you can try to see what happens for L equal to 5, for example. That is odd, because in this case, we were using even length, so the number of U that we get in both rows are the same. But if it's different, maybe something else will come out. Yeah. Sure. Up, down. Okay. Which one?
After taking the test.
Here? Like here? From here to this. So I just put this P at the very end. So this P06, and then all the time there was a 0, this becomes a 6. So I got P65, 64, 63, 62, 61, 4, 5, 2, 3, and here that 0 also becomes a 6. And then it remains this permutation which we put at the end, and this traces to 1. Yeah. Okay, so maybe I can just give you an explicit example on how to construct one of these circuits for one of the model that we, for the Heisenberg model that we saw, and I can tell you how the kappa is related to the time, so we can finish the story. Let me see. Okay. So up to now, everything was general for any model, solution of Yang-Baxter. Let's focus on the example that we discussed yesterday. Example XXX model.
Sorry, so when you are saying that you put P06 to the last one, I don't really follow how those P05, P004, those gets changed to P65.
So if the P06 you move to right, P05 becomes P65.
Oh, okay,
Yeah.
those are not in the same space.
And then those, yeah. Okay.
So even in non-integrable model, the statement is that this M cannot be constructed as a function of transfer matrices.
Yes, I mean you can play this game for some R matrix which do not solve Yang-Baxter equation, and then you write this as this function of transfer matrix, but you don't gain anything because the two transfer won't commute, so you don't get conserved charge.
There exists at least one M such that it commutes with all the charges. The second thing is, so is that unique, or is there other ways of doing it?
I mean, you can, you are asking for this choice of inhomogeneity. So if you want to construct that geometry, then this is the choice, like this TU inverse. Or you can, for example, construct the other way around, U odd, U even, if you place it differently. Yeah, I don't see what else you can get. So yeah, I will guess it's unique, but I will have to think, yes. Other thing that you can try to play it with, for example, just to take a bit of practice with these indices is what happens if, for example, you make this choice of inhomogeneity. You take U1 equal to U2 equal to kappa, and then you take U3 equal to minus kappa, and then with periodicity, so U4, U5, and then here you take U6. You will get some different gate configuration. I think the one corresponding to these 3, 4, 5, 6 is probably something like this. It's swap 1 and then this, and then there is these things here. And then you repeat this game multiple times, but you have to try with the indices. Or if you are interested in playing this game, I can tell you some trick later on how from this guess you can get a circuit. Okay, but let me do the example of the XXX model. So for the XXX model, we say that the R matrix of U is equal to U identity plus IP. And to have unitary dynamics, R check of 2 kappa can be written in this form: 1 A B A B 1. Sorry, A B, and A will be equal to 1. This is the same definition as yesterday, but written in terms of kappa now. 1 plus 2 I kappa, and then we have the property that A plus B is equal to 1. Okay, so if I take now this R check of 2 kappa, we can see that if we expand, so R at 0 is the permutation, right? So what is R check at 0? It's 1, yes. So this is 1. And then there is plus 2I kappa H. So if you expand this one explicitly, you will get permutation minus identity, which is the Heisenberg-Hamiltonian. Heisenberg. Plus other term. I think this is easy to see because we were also showing that the H is related to the first derivative of the R. So it's always the same thing, but put in different ways. So we did this. So R, the first, so which one? R and R check. So R is just a PR check, or R check is a PR. Yes, okay. So you can try for the M that is given there, e to the minus, this is U odd, U even, and then we expand for small kappa, and this is just 1 minus, then the parameter of expansion is 2 kappa. Then there is I, because we had IT. H plus any higher order term. So the expansion of this will be like describe your system for discrete time for small t. But if you take expansion and you take this time, this is our time now, tau. You take this time to be small, then you get the continuous time evolution as expected. So nothing strange happen. But let me just give you another. So this is the example that we gave yesterday. You can also have another R matrix to construct your circuit. And I want to give this one because I want to give you two references on how really people computed some quantities by using this quantum circuit. So the other example is this XXZ spin chain. The expansion is this R check of lambda.
Sorry,
Yeah.
before you go there, how did from the first line, second line form your expression of n?
Yeah, I didn't write it explicitly. So this you can get this one if I take UO to be so UO was U65 U4 U34. Sorry, here I can always do this U12, and then you use in this one you plug this expansion because this is U. And then you will see that the first order will be this one. So you can interpret this 2 kappa as time. And I forgot to say that, yeah, kappa I will take real. Real parameter, yes. To have unitary evolution.
What did you write there? E minus 1 each?
Because this one I took the, because yeah, this one if you write explicitly the definition of A and you expand, then you get this term, and this is the Heisenberg Hamiltonian which we wrote yesterday. And okay, yeah, I will just in a few minutes give this other R matrix. You can maybe try to construct this object in Mathematica and check Yang-Baxter equation. And you can maybe construct the charges if you wish. So this is 0, 0, 0, 0, 1, 0, 0. These entries here is sine of lambda over sine of lambda plus eta. This is this one here will be the same, so I will not write for space reason. This is sine of eta divided by sine of lambda plus eta. And this one over there is the same as this. Sorry for this. So the structure is the same as this. These two are the same, these two are different. The denominator is the same. This is sine of lambda, this is sine of eta. Yeah.
So this case, is it the generalized unitary evolution?
Yes. So if you take U to be unitary, then you can, yeah, M will be unitary as well.
And for integrable circuits, this should like commutator with this with Q is give 0. Is this the same?
Yeah. So now for integrable circuit, the commutator of M with all Qi will be 0. But yeah, thank you actually for the question, because I was not very precise. Yeah, because now for an integrable circuit we have constructed it in a way for M to commute with the infinite amount of conserved charges. But are these charges the same as we had before or not? Thank you. Yeah, important. I forgot to say. Are they? It's a bit tricky point because
It depends on like, it depends on the functional form, right? Because you have to collect the coefficient of the U and U squared, so it might change it.
yeah, good. Yes, they will change because okay. So this is the XXZ spin chain. Then there is an exercise on the tutorial that on which limit you have to take on this R to go back to the XXX model. Yeah, in these remaining minutes, I will just tell you about this locality of charges, and then next time I will give the reference for that, for what people computed with this type of models.
So what was this again? This XZ in the XZ case?
Yeah, so I wanted to just give you that model because I want to give some reference where people computed some quantities. Maybe you were interested in some, I don't know, experiment or some concrete computation, and they use this R to build the following circuit. But yeah, let me just mention about the charges. So yesterday we took the transfer matrix and we put all the inhomogeneities to be equal to 0. And then we showed that all these charges can be written as sum of density term that act on some given support. Now the story is the same, but what we are doing now is that TU, UI, TV, UI, this is equal to 0. But this is equal to 0 only if this set of parameters are the same. So yesterday we had all this set of parameters to be equal to 0. Today we have this set to be equal to U1, equal to U3, equal to U5, equal to kappa, U2, or maybe minus kappa, U2 equal to U4, U6 equal to plus kappa. So you can always take the log of this TU for U equal to 0, and you will get some operator, some charge Q. But which index do you put there? This is a question, right? Because before the first derivative of log of t was Q2, but now what it is? So for circuit, I will show you next time that the first charge here will have these indices to be 3. And if you want there is no time, so I will not give you the expression, I will give you next time. But maybe you can think, you can think about some reason of why the first charge has to be written as a density of range 3. And just to mention, actually for circuit, I will show next time that the set of charge, there are two sets of charges which can be derived in this way. You take n minus 1 derivative of log of tu, and then you fix u to be equal to plus or minus kappa. This will give two sets of conserved charges which will commute among themselves. And that will commute among themselves. It will commute with the circuit dynamical evolution. So the circuit will be integrable because it exists a set of infinite amount of extensive conserved charges.
So here this Qn doesn't refer to the n-body terms, right?
It does, but it does not as before. It was starting from 2. Now, if you take the first derivative of this log, it will start from 3. I won't have the time now to explain, but you can maybe think about it. Maybe you get some intuition. I can tell you next time otherwise. Are there questions?
For the x-axis region, how have you taken these Q values given to x-axis?
For x-axis, how the
that right side is not written Q1
x-axis or?
x-axis.
Mm-hmm.
U1 into U3 equals to U3 equal to U6 equal to minus k and others are k. So how have you taken these two?
So U, I'm not sure if I got this U equal to identity plus 2I kappa. This is the question.
And the right side that this go down. Can you go up?
Yeah. Down? Yeah.
This circle is drawn and Q value sets
This one.
that circle.
This. Up. Which this one? Ah, sorry. Yeah, I didn't specify. Like I just told that if you want to take a little bit of practice with these indices, you can try to play the same game as we did, but with different indices. I mean, if you are interested, you can look at. We have a work about this together with Lennart, Zadnik, Urban Du, Balázs Posgai, and me, where we prove that if you take any solution of the Yang-Baxter equation, you can place the gate in different place, but in every period, one gate has to be placed exactly 1 times. And we have proven that all of these circuits with different geometry are all Yang-Baxter integrable. So if you take a look at the paper, there are some explicit examples on how you place this value of inhomogeneity and how from that you get the different geometry. So yeah, here I didn't derive because it takes a bit of time. Yeah.
What was the actual parameters eta and lambda in the x-axis speech?
Yeah, so lambda will be the same as u that we had before, and this eta will be related to the so the Hamiltonian will have this form x1, x2, y1, y2, and then there is a delta z1, z2. I think, let me check, delta is equal to cos of eta. Yeah. U is lambda, yes. Just, to create more confusion, I'm starting to adding parameters, but you can call as you wish.
Given a Hamiltonian, can we write explicitly always this R?
I will show in the tutorial how to do. Yes, it's a one-to-one mapping. On how, if the Hamiltonian belong to a Yang-Baxter model, you can always write there.
Then we get R
And then you make the circuit, yes. Building block is R matrix that solves Yang-Baxter. If you have that, then you finished. Yep.
Okay, so there is one more question. So last one, please.
Yep.
Using this formality, you can get circuits with integrable circuits with two-body operators. So, like, is there a way to get like three-body operator integrable circuits or something like that?
You can, yes. In this paper that I was showing you before, they construct integrable circuit with range 3 operator, and then you can generalize to higher. Yes.
Okay, so let us thank Chiara for the beautiful lecture.
Thank you.